Welcome, and thanks for joining us. I'm excited to be here. We have lots of exciting content planned for this session and some pretty cool announcements to make as well. My name is Edward Name, and I lead the product management team for EFS. I'm joined on stage with Daryl Osborne, who's a solutions architect, a storage solutions architect at AWS. We have so much content that we likely will take the entire 60 minutes to go through it. So in terms of Q&A, feel free at the end to come up, and Daryl and I will stick around for 15, 20, 30 minutes, however long it takes to answer your questions one-on-one. Let me start with a quick run-through of what you can expect during the session. I'm going to start by talking about EFS, give an overview of EFS, and talk about why and when you would use EFS. I'm going to review some key technical and security concepts. Some of that material will be refresher content for some of you, but I want to make sure we all have the same baseline of knowledge before we get into some of the deeper sections. Then I'm going to spend time talking about EFS performance and a number of aspects of our overall performance model and how you can leverage that performance model to really optimize how your applications and workloads run with EFS. Then we're going to do two hands-on type of activities. Daryl's going to walk through a real-world example of how you can move data as quickly as possible into EFS and between EFS file systems using parallelization. And then Daryl's also going to talk about a WORDPRESS example. He's going to go through what it's like to deploy WORDPRESS onto EFS and some of the best practices for that. We're then going to talk about EFS's economics, so I'll talk a bit about total cost of ownership and how to think about that. And then we have some exciting feature plans and announcements to make. So let's get started. And let me start by talking about AWS's storage offerings, its overall portfolio of storage products, and how EFS fits into that set of offerings. AWS offers three main types of storage: file, object, and block. And let me walk through each of those in turn. So starting from the right, block storage, which is represented by Amazon EBS and EC2 instance storage. With block storage, data is presented to an EC2 instance as a disk volume. And block storage provides that disk volume to single instances and provides the lowest latency that you can get from any of our storage products for operations. So EBS, for example, is really popular for boot volumes and for database workloads because of its low latency. And we have object storage. So an object is a piece of data, like a document or an image or a video file, that's stored with some metadata in a flat structure. And object storage provides that data to your applications via an API over the internet. So with our S3 service, it's super simple to build, for example, a web application that delivers content to your users by making basic API calls, GET calls to your bucket of storage. Glacier also is object storage, and it's intended for archival use cases. So it's really intended for data that's accessed infrequently, and you're able to pay a lower price per gigabyte for that data for storing it on AWS. And as of 5 months ago yesterday actually, with the announcement of EFS as a generally available service, we now have file storage. And with file storage, with EFS, data is presented via a file system interface and file system semantics to EC2 instances. When it's attached to an EC2 instance, your EFS file system acts just like a local file system would. And with EFS, you can attach your file system to one, a few, tens, hundreds, thousands of instances so that all of these instances have access to the same set of data. And there's strong consistency across the accesses for operations across those instances. With EFS, we focused on changing the game for file storage and for storage in general. And there are three core pillars to our design of EFS. The first is that EFS is simple. The second is that EFS is elastic. And the third is that EFS is scalable. And those three are on top of a foundation of high availability and high durability. And let me talk about each of these in turn. So EFS is simple. It's a fully managed service, which makes it easy and simple to administer file systems at scale. There's no file layer or hardware to manage. There's no volumes, LUNs, RAID groups, provisioning to manage, none of that stuff. And with EFS, you can create a file system in seconds. And that's probably hard to believe for some of you who have built your own file storage on top of AWS or outside of AWS. But it's really easy to get started. And we'll talk a little bit about that a little later. EFS provides seamless integration with existing tools and applications. It supports NFS version 4.1, which is a widespread and open protocol. It provides standard file system access semantics. So you get what you would expect from a file system, the ability to take out locks, the ability to write data to the middle of the file, the ability to append data to the end of a file, directory structures, atomic renames, strong read-after-write consistency. And it offers simple pricing. It's a simple cents per gigabyte per month model that incorporates all of the charges that you would incur. So there's no charges for throughput, there's no charges for request pricing. It's just a simple 30 cents per gigabyte per month. Having a little trouble with the clicker here. Okay. EFS is elastic. So file systems grow and shrink automatically as you add and remove files. There's no need to provision. In fact, there's no way to provision storage capacity or performance. Things just scale up and scale down as you add data and remove data. And you pay only for the storage space you use. So you literally are paying just for the bytes that you're storing on EFS. And EFS is scalable. File systems can grow to petabytes of capacity, and there's no need to reprovision as your file system grows, no need to adjust performance settings, no need to really do anything for your file system to grow to petabyte scale. It just does it automatically as you add data. Throughput scales automatically as file systems grow. So with every gigabyte of data that you store, you get a certain amount of throughput that you're allowed to drive to EFS. So that means that as your file systems grow, the amount of throughput that you can drive in order to read data and write data grows with the size of the file system. Provides consistent low latencies. Lots of file workloads are latency sensitive, so it was really critical for us to make sure that we offered consistent low latencies. And EFS supports up to thousands of concurrent NFS connections. So if you have applications that span multiple EC2 instances, they can all have access to a common set of data. And EFS is designed to be highly available and highly durable. Your data is automatically spread across multiple AZs, and it's available in multiple AZs. So you can read your data and write your data from any AZ within a region. And every aspect of the service, beyond even just the data, is designed for high availability. So including the endpoints that you create in your VPC, which I'll talk about in a second. So where can you use EFS today? We're in 4 regions: US West Oregon, US East Northern Virginia, US East Ohio, and EU Ireland. And there are many more regions coming soon. And a question I sometimes get is, should I use EFS or should I use EBS? And with EBS, you can format your volume with a file system. So when would you use EFS versus EBS? Well, some guidelines to think about when you're trying to figure out does EFS make sense is the following. So if you have an EC2 application and it requires a file system and either requires multi-attach, so requires access from more than one instance, requires multi-AZ availability or durability, needs to scale to gigabytes per second of throughput, or if it requires automatic scaling, so as you add data, it grows, and as you take it out, it removes. So if you go through that and you meet any of those, you should really consider EFS for your application. And we'll talk a little bit more later on about EFS and EBS and some of the differences for you to think about. And you should understand that operating your own file storage is complex and it's expensive. And there's really two ways that people typically do that. So one is you can simply replicate EBS volumes. So for example, let's say that you have a web serving environment, you have multiple EC2 instances, and on each instance you're running an Apache web server, and you want each of those web servers to have access to the content that the web server needs to serve. So you could go and create an EBS volume, attach a different volume to each instance, and synchronize your files across volumes. The problem with that is that there's a lot of management overhead in doing that. You need to manage the syncing of data, you need to provision and manage volumes, and it's also expensive because you're paying for at least one volume for every web server that you have. Another way to have your own sort of file storage on the cloud that's accessible to multiple instances is if you use an NFS server. You set up your own NFS server on an EC2 instance, or you use a shared file layer. So some third parties offer shared file layers that you can install on an EC2 instance and that are backed by EBS volumes. So those solutions, unfortunately, in many cases are complex to set up, complex to maintain. It's not a fully managed service. You run into scale challenges. Think about the case of a single NFS server running on a single EC2 instance. It's running on a single box, so there's only so much scale that you can have. Similarly, there's challenges around high availability. Again, if you have a single box or even a small set of boxes, you're introducing some availability risks. And those solutions are costly, and we'll talk about cost in more detail later on. And customers are using EFS for a wide variety of workloads and applications today. Web serving, content management are super popular use cases for EFS. So a lot of customers that are doing database backups of EBS volumes onto EFS. Analytics workloads are really popular, so you'll have tens or hundreds of instances that are doing analysis on a common set of data. Media and entertainment workflows like video processing, video transcoding, container storage, home directories, and really many different types of workflow management where you need to share some data or some set of state across an application that's running on multiple instances. Okay, so let's talk briefly about some key technical and security concepts. And let me start, this clicker's still acting up. Let me start with a definition. The fundamental EFS resource is a file system. And that's where you store your files and your directories. And you can create 125 file systems per account. And then, let me just take care of one thing. Sorry. Another definition is a mount target. So you access your file systems from within a VPC, from instances that are in a VPC. And in order to do that, you create these endpoints, which we call mount targets, in HAZ within a VPC, from which you want to access an EFS file system. And what this endpoint or what this mount target does is it provides an IP address and it provides a DNS name that you use when you're mounting your file system. And mount targets are designed to be highly available. And how do you access a file system from an instance? Well, you mount it using a standard Linux mount command. And if you can make that out on the screen here, it's there's the command up there. The -T is the means that you'll specify the type of mount, and that's really the only parameter you really, or sorry, one of two parameters that you need to specify. So it's an NFS4 mount. And then an optional parameter that you need to specify is the NFS version number, which is 4.1. And we highly recommend 4.1. We do support 4.0, but for performance reasons, 4.1 is what we recommend. Then you provide the file system DNS name, which is what the mount target provides. And you could replace that with an IP address for the mount target as well, if you prefer. And then the -O is for an optional parameter, which I mentioned, the NFS version number, and then the user's target directory, the final parameter there, and that's the local directory that your EFS file system will appear in once it's mounted. Okay, so how does it all fit together? So you have a region, and within a region you have a file system. So file system it belongs in a region. You have a VPC in that region. That's your VPC. And within each AZ, you create these mount targets in your VPC. And the EC2 instances that are running in the AZs in your VPC connect via those mount targets. And you should note that data can be accessed from any AZ in the region concurrently while maintaining full consistency. So if you're doing writes in one AZ, you're guaranteed that the reads in another AZ will have the latest version of the data. And there are a number of security mechanisms available to your EFS file system. So first, at the network level, you can control network traffic to and from your file systems by using VPC security groups and using VPC network ACLs. And really what you're doing is you're applying, with the security groups, you're applying them to the mount targets. And so because the mount target is where you're sending your traffic to the file system, you control what traffic can reach your file system by applying the relevant security groups to those mount targets. You can control, at the data access layer, file and directory access by using POSIX permissions, standard POSIX permissions. And then at the administrative level, you can control API access to file systems using IAM. And EFS supports both action level and resource level permissions. And then what does our API provide? Provides basic management functionality for your file system. So the ability to create a file system, create and delete mount targets, tag a file system, view details on the file systems in your account. And those, the API functions are accessible through our UI, through the management console, through the CLI, and through the SDK. Okay, so let's talk about performance. EFS is designed for a wide spectrum of performance needs. And if you think about a typical way that people think about performance across a spectrum, on one side you have applications and workloads that drive high levels of throughput, often from many instances, so a lot of parallel operations. And the name of the game is as much aggregate throughput as possible across a number of instances. And then on the other end of the spectrum are applications where you're doing a lot of serialized operations, and the latency of each individual operation makes a big difference in terms of how many operations per second or how much throughput you can drive. So very latency sensitive applications. And what you see on the screen here in terms of workloads are examples of what customers are using EFS for. I talked about a couple of these before, but on the throughput intense side of the spectrum, things like genomics workloads, big data analytics, scale-out jobs. On the other side, metadata-intensive jobs. And then sort of in the middle are a lot of the sort of general types of use cases that you would use file for. So web serving, content management, home directory, et cetera. And in order to support that spectrum of workloads and applications, EFS offers two different performance modes that you can choose from. So the first is called general purpose mode, and that's the default mode for a file system. And what it does is it offers the lowest latency for your file operations. Now the trade-off for general purpose mode is that there's a limit in terms of the number of operations per second you can drive when you're in general purpose mode. And that limit is 7,000 operations per second. The other mode is max I/O mode, and it offers a virtually unlimited ability to scale your throughput and IOPS. So you don't have this 7,000 operations per second limit, but the trade-off is it does so with slightly higher latencies per operation. So in terms of which workloads make sense for which performance mode, in general purpose mode is the best choice for most workloads. That's why we call it general purpose, and that's why it's the default. But if you need high aggregate levels of IOPS or high aggregate levels of throughput, and typically that's if you have a workload, for example, where you'll have tens or more instances accessing a file system and driving lots of traffic to it, then you should consider max IO mode. And what we generally recommend is when you're testing EFS with your application and trying to figure out should you use general purpose or max IO mode, you should start off by creating a file system that's in general purpose mode and testing it. And we provide a CloudWatch metric that shows how close you're getting to the 7,000 operations per second limit that's tied to general purpose mode. So we recommend just testing it and looking at the CloudWatch metric to see. And if you're okay in terms of CloudWatch metric, you should definitely stay in general purpose mode. In order to understand EFS's performance model, it's helpful for me to provide a bit of context on EFS's architecture. So EFS has a distributed data storage design. And what that means is that file systems are distributed across an unconstrained number of servers. And why that's good is because it avoids the bottlenecks and the constraints of traditional file servers. And it allows high levels of aggregate operations per second and aggregate throughput, and also allows that scaling to petabyte scale that I talked about. With EFS, as I mentioned earlier, data is also distributed across availability zones. And that's important for durability and availability. So when you do a read operation on EFS and you get the acknowledgement back that the write operation has completed, you can be rest assured that actually the data has been written across multiple AZs. So that happens before you get the acknowledgement back. Now, this distributed architecture has some performance implications. So one is that there's a small latency overhead for each file operation. And that's tied to the fact that the data is spread out, and it's spread across multiple availability zones. And it's strongly consistent, so when you get an acknowledgement back, you know the data has traveled to the other availability zones. But it also enables scale out. So it allows you to get to these high aggregate levels of performance. And so when you think about EFS versus EBS, it's helpful to think about a few different things. So the first is the per operation latency. So EFS does offer low consistent latencies, but because of the distributed design I just talked about, if you're looking for the absolute lowest possible latencies, EBS has lower latencies because it doesn't have that distributed design. In terms of throughput scale, EFS scales to multiple gigabytes per second. And Darryl will talk about, he'll give an example actually of a couple gigabytes per second that he drove when copying data on EFS. With EBS, it's around a single gigabyte per second. In terms of availability, durability, EFS, data spread across multiple AZs. EBS, it's in a single AZ. Access, EBS, single EC2 instance can access a volume. With EFS, you can have 1 to thousands of EC2 instances accessing it concurrently. And so some of the use cases that are really in the sweet spot for EFS are big data and analytics, some of the media processing that I was talking about, content management, home directories. With EBS, really latency-sensitive applications like databases make a lot of sense for EBS, and EBS also makes a lot of sense for boot volumes. Tied to this per operation latency that I've been talking about, the overall throughput that you can achieve when you are doing a sequence of operations in serial across EFS is tied to the size of the operation that you're driving. So if you're doing a read or a write that's a read or a write of a bigger piece of data, that latency is amortized over a larger amount of data. And so in effect, if you're doing these operations in serial, you're able to drive higher amounts of throughput with larger operation sizes. And this graph shows I/O size versus throughput to give you a sense for, and again, this is a serialized operation, to give you a sense for what that looks like. And EFS is designed to process high volumes of concurrent operations in an effective way. So one way to drive high levels of throughput or high levels of IOPS is to do it via parallel operations that you're throwing at EFS concurrently. And you can do that via multiple threads on a single EC2 instance, or if you want even more parallelization, you can do it on multiple threads across multiple EC2 instances. And this graph illustrates that. So in this graph, we held the I/O size constant. It's actually, we're showing the creation of 4K files. And this is across 10 instances. And it shows on the x-axis the number of threads, and on the y-axis the aggregate IOPS that you're able to drive. And in this example, you can see almost a linear increase in the aggregate IOPS as you increase the number of threads. And Daryl's going to give a little bit of a walkthrough of an example of doing some of this parallelization, so you can see how you could actually do that in the real world. And we provide CloudWatch metrics for a variety of views of your file system performance. If you want to understand the operations per second that you're driving, if you want to understand the volume of throughput that you're driving over a period of time, we have CloudWatch metrics that provide that data. Two metrics that I'll call out specifically: burst credit balance and permitted throughput. As I mentioned, the amount of throughput that you're entitled to on an EFS file system is tied to the amount of data that you're storing. And essentially, the rate at which, so we have this burst credit model, and if you have burst credits available, you're able to drive throughput to your file system. And the rate at which you earn these burst credits is tied to the amount of storage that you have in the file system. And it all equates to around 100 megabytes per second of throughput that you can drive for every terabyte of data stored. So if you have 1 terabyte, it's 100 megabytes per second. If you have 5 terabytes, it's 500 megabytes per second. And there's details in our documentation on this, but just wanted to give you a feel for what that bursting model is like. And these two CloudWatch metrics, the burst credit balance, permitted throughput, give you visibility into how you're doing from a burst credit perspective, and if you're okay, or if you need to add more data in order to get the level of throughput that you want. And then in terms of kernel version and NFS mount options, these things actually really matter. So definitely use a Linux kernel version 4.0 or newer. There's so many performance enhancements that have been added to the Linux kernel over time. So we highly recommend 4.0 or later. And mount via NFS 4.1. There are a bunch of performance enhancements tied to 4.1 versus 4.0. Including improved performance for multi-threaded applications. So that's something we highly recommend. The other parameters that I'm showing, the other optional parameters, you don't need to worry too much about because those are the defaults for most clients. Doesn't hurt to specify them anyway in case it's not the default for whatever client you're using. But all of this stuff is in our documentation as well. But for the most part, default options will be what you need. So a summary on the performance front. First of all, test, test, test. I can talk about latencies all day. I can talk about throughput all day. You're not going to really know what that means for your application until you test your application. That's because every application has a different set of access patterns. So testing is really the best way to understand what does your application look like when working with EFS. Use general purpose mode for lowest latency, max I/O mode for scale out. And for most use cases, general purpose mode is the right mode. Use kernel version 4.0 or later, NFS 4.1. Look for opportunities to aggregate your I/O, so use larger I/O sizes when you're reading and writing data. Perform asynchronous operations. So one parameter I sort of glossed over on the previous slide was the async mount option, which is a default mount option. And what that does is it allows the NFS client to acknowledge a write even before it's gone to the back end. So that gives you some enhanced performance for writes, and also similarly for reads. But there's some you need to make sure that you're okay from a consistency perspective in order to do that, because you'll be getting acknowledgments to your application that a write is completed, even though it hasn't propagated necessarily to the back end. Parallelization, we'll talk about that in a little bit, and then we'll also talk about using caching in front of your file system. And with that, I'll turn it over to Daryl.
Thanks, Ed. Appreciate it. So welcome, everyone. Glad to be here. I'm from Texas, and in Texas, we love things. Who else is from Texas? Any Texans here? All right. In Texas, what do we like? Things in Texas are bigger. And in Texas, we like things faster as well. So what do we want to do? We want to move a lot of data, big data, very fast. So that's what I wanted to do. So this is what we did. We had two scenarios. The first scenario was we wanted to transfer a lot of media assets. So what we did, we came up with a random size file. So they range from 1 gig to 100 gig plus. We wanted to move them from S3 and EBS. Our next scenario is we had a lot of smaller files. So we randomly generated files between 64K and 256. And again, we wanted to transfer those from S3 and EBS over to EFS. So how should we do this? Do we want to parallelize the copy, or do we want to do it in a serial manner? So if we take a look at serial, what does that look like? One file after another. So you can only do so much activity at once. Or should we do it in parallel? Have a lot of different threads. Have a lot of different instances doing this copy at the same time. So what did we use? We used new parallel. Some of you may be familiar with this. You could be familiar with XArgs as well. So very similar to that. So it really replaces having to loop through and do basically a copy command. So what we did is, and it talks about it, with new parallel, it makes it it's consistent because the output is going to be the same as if you did it in a serialized manner. All right, so this is what we did. We created the destination directories using parallel, and we did the copy as well. So what does that look like? So if you're familiar with AWS, we love data. We thrive for data. So data tells us so much information about how things are going. So we wanted to have data-driven results. We also wanted to hand this off to someone else. We wanted a repeatable output, results. And of course, we want to make sure that we're optimizing for cost. We want to do this as inexpensively as we possibly could. So we wanted to determine the best instance type to help us with reducing the cost, but we wanted to make sure that we could move a lot of data very, very fast. So we looked at these families, these instance families, and we wanted to see which is going to be the best. We wanted to do a quick test transfer of 1,000 files, and we wanted to take a look at the different threads. If we went from 1 thread to 1,024 threads, what would that look like? How would that impact this copy, this transfer? So we used a couple of tools to do this. We used Datadog to monitor the performance on the instance. We used Sumo Logic to do the data visualization. And we also used Salt Stack to do the automation, the orchestration. So what happened? So with 4 instances, we were able to run 451 megabytes a second. And it looked something like this. We had very consistent throughput for all 4 instances. That's great. But what does that mean? How can we improve that? So again, if we go parallel, we want to add more instances. If we went up to 50 instances, we were able to get 4.2 gigabytes a second. Now, that's not the limit for EFS. That was the limit for our environment based on the size of data we had stored in our EFS file system. So if you have more data, you can definitely see that throughput increase. Now, let's go to our other use case, our other example, our scenario. So we had a lot of small files, ranging from 64K to 256K. And we wanted to see which instance type was going to be best and how many threads we should be using. So all the different colors you see here, those are all the different instance types we ran this test against. And if you notice, right there at about 200 threads, it sort of plateaued off. So now we know, you know what? 200 threads is where we want to be for our use case, for our example, our workload. So we wanted to find the best instance type at the least cost. So that brought us to the C3 large instance type. And we were able to push through 5,000, a little over 5,000 files per minute when we did this at 200 threads. All right, so now we have the optimal instance size. We have the optimal number of threads. So now what we want to do is we want to go parallel. We want to increase the number of instances. So we decided, let's go ahead and try out 300. Oh, and also we want to optimize for cost. So what did we use? Spot market. So what does that look like? Cost-wise, this cost to do this test, it's around less than $5 to run this test. These instances were running at 4.5 cents per hour. So we were able to do this test very efficiently. With 300 instances, this C3 large instance, we were able to copy 1.6 million files a minute. So that's a lot. So that is parallelism with the optimal instance type with the number of threads and the number of, the correct number of EC2 instances for our workload. And you can see it very consistent for all of those EC2 instances. So in summary, what did we learn from this? Very large files, we can get a lot of throughput. Here we were limited to 4.2 just because of the size of our file system, but definitely that can increase if you have a larger file system. And with small files, again, you want to go parallel. Increase the number of threads. You want to increase the number of instances. And you can also start pushing, depending on your workload, your use case, you can see performance similar to this. So, in summary, we want to parallelize everything. Parallelize threads, parallelize instances. As Ed mentioned, you want to test, test, test. Test your application out. Test it again and test it again. Make sure it's working the way that you want it to. You want to capture and analyze this data as well. You want to see how are you performing when you're running your workload against EFS. And again, to do this test, it costs us less than $5. All right, so that sort of showed you a little of how we recommend to run a sort of a parallel workload with threads and instance counts. Now I want to talk a little bit about a good use case. So Ed mentioned a number of different use cases that EFS is really great at serving. And one of those, is sort of a combination, is content management as well as web serving. So you're all familiar with what this is. You know, it's basically a web-based application serving out content. This could be wikis. This could be blogs, you know, just web applications. So one that is very popular, and you may be familiar with, is WordPress. So WordPress, as you may be familiar with, it is a free and open source tool that many people, who's running WordPress today? Got a couple WordPress users out there? Okay, great. It's great software. It really makes your web page look great, very easy to run. Free and priceless is the quote from WordPress. So it's a great product. As I looked into this a little bit more, I was surprised at the number of sites that actually run WordPress. So there's a study just done recently that said that 27% of all the websites are running WordPress. That's amazing. 27% of anything in this market is huge. So that's great. There's also a quote or a study done that it says it's very easy. So it's very easy to run, very easy to maintain. And again, another study from Forbes. This was a little while ago, so it's probably a little out of date. But it also said that there's 60 million websites are running WordPress. So we want to test this out. How would this great web serving content management system perform on EFS? So WordPress is available in really two different flavors in a sense. So if you want to run a WordPress site, you can go to a managed provider. So WordPress.com is one, Press.net is another. There's just two that I'm familiar with. But there's hundreds out there that will manage and basically provide the WordPress environment for you if you wanted to run your application there. The other way is to download the software from WordPress.org and run it yourself. So that's what we're going to do today. So we want to do a comparison between resources and components of WordPress, so how they sort of map. So if we take a look at this, unstructured data, we want all that unstructured data in components, and we also want the structured data under the components of WordPress. Where is that going to go to, where's that going to be stored in AWS? So the unstructured data is going to be in EFS. That's where we're going to store those PHP files, the themes, the plugins. Those are some of the challenges that a lot of users, administrators have, is when they start installing these plugins and themes, it's going to be installed on maybe that local instance. And then you got to do that multiple times as you sort of expand your WordPress fleet. So we want to store that in a file system that is shared among a number of EC2 instances. And that structured data we're going to put in RDS, of course. So what does this look like? So very quickly, this is the architecture that we're going to be coming out with, a reference architecture with this and an updated WordPress white paper that has all this information in it. So within your VPC, you're going to have a couple of AZs. You're going to have those mount targets that Ed mentioned. They're going to be connected back to your EFS file system. You're going to have RDS spun up. You're going to have an EC2 instance. And that EC2 instance is going to be able to connect to the mount target as well as your RDS environment. But we want to do more than just one instance. So we want to have an auto-scaling group, and we want to have multiple instances in there. In front of that, what do we want? We want ELB. We want this to be connected to the internet. We can put CloudFront in front of that. We can put RDS or Route 53, and then our users will be able to connect. We can expand this a little further and actually cache some of the database data, that structured data. And we can put Elasticache in front of RDS. Then to also help out, what we can do is install OP cache on the web servers, on our WordPress servers, to cache some of those PHP files from EFS. So what does this look like? So let's go ahead and very quickly take a look at this. So there we go. This is an example of a CloudFormation template that's going to be included in the reference architecture. These are just some of the configuration settings, the parameters that we have. So we want to identify the file system name, the performance mode, general purpose or max IO, all the NFS mount name, then go into the VPC configuration, the WordPress configuration, ELB configuration, Aurora, we're going to put this in an Aurora cluster. Elasticache configuration as well. So all of these parameters are going to be in this CloudFormation template. Okay. So we're not going to run that right now, just because it's going to take some time to create the RDS Aurora cluster. So we're just going to go ahead and jump over to an environment that's already up and running. Now I have this over in the Oregon region. So what does this look like? So if we take a look at our load balancer. So right now we have one WordPress instance. And when we launched that CloudFormation template, what it did, it actually mounted that file system as well, installed all the applications that we needed. So if we take a look at the dashboard for WordPress, we want to go ahead and install a new theme. So let's go ahead and do that. I like this theme, so we'll go ahead and use that. So this is going to be downloading, and it's going to be downloaded and installed on our file systems that's mounted to this, this one single instance that's serving up all of our WordPress content. Now that that's installed, we're going to go ahead and activate it. Now what we can do is take a look at what that looks like. So very simple, very basic WordPress site, sort of out of the box. Well, we also want to install some plugins as well. So we want to add a new plugin, and we want to add the OP cache dashboard. So again, very easy to do the installation. Again, this is going to be installed. It's going to be stored in our WP content folder, which is sitting on our EFS file system. Let's go ahead and activate that. We also want to activate our other plugin. Our W3 Total Cache plugin as well. So now that that is working, what we want to do is we want to make one small change. And this is something you probably wouldn't do on your side. But you notice here, if we don't know exactly what instance this is running on. We only have one instance, so we know it's running on that one. But if we expand our auto-scaling group, we're not going to know what instance that is. So quickly, I'm going to go ahead and just copy a header file that I've already made some changes to. And actually, first, we need to go ahead and connect to that EC2 instance. Grab this instance, we'll go ahead and connect to it. Grab our connection string. Now, let's go ahead and copy that new header file over. So now, what do we have? If we do a refresh on this, now we're going to see the instance ID. So that's good. So now we know that it's running there. But we want to do something else as well. So let's go ahead. Let's add a picture. We want to make, we want to customize this just a little bit. So let's go ahead and select a file. We'll upload a new file. And my site is called Cloud Viking. So we've got a little picture of a Viking ship. We'll go ahead and save that. We want to use logo and tagline. Save and publish. Now, as we refresh this, we're going to have our little picture, which is great. So now, let's say that we have an event, an auto-scaling event, that we needed to expand our auto-scaling group and have launch a number of other instances. So if we go into our auto-scaling group for this environment, We'll change the desired number of instances to say 4. Go ahead and save that change. So now in the background, it's going to automatically launch these instances. Well, a part of this, the launch config for our auto-scaling group, has all the information it needs to download all the files it needed to for our environment. It's able to automatically mount the EFS file system, and it's going to be automatically joined to our load balancer. So if we quickly switch back to our environment, one thing we could also do after we've done all this is we could install our memcached client on our EC2 instances. We could configure OP cache a little bit more and say, you know what, we're going to maybe attach another EBS volume and actually have OP cache store those files, cache those files on this other EBS volume if we wanted to. We could also use CloudFront to cache some of that information and use that as our CDN. Then we could also use Route 53 and put in a custom domain name. So this would look like any typical WordPress application, but in the background, you have basically an infinite number of EC2 instances that you could scale to, an infinite amount of storage in EFS, and on the database side, you've got an Aurora cluster, but in front of that, you have an Elasticache caching mechanism to cache all those database calls. And again, both of those environments can grow if we need to. So now if we quickly hop over to see where we're at, hopefully all of those instances have joined. It looks like successful. Now if we hop back and we do...
Change the input.
Oh, yeah. Thanks. Now if we hop back and we take a look at this, take a look at the instance ID, and as we scroll through this, we should see the instance ID change. So now all of these instance IDs, these new instances, have been added to our load balancer, and it's serving out all of this data. Again, very easy to deploy. We have this in a CloudFormation template. It's going to be available as a reference architecture, and we're going to be updating the white paper as well.
All right. Thank you, Daryl. All right, so let's briefly talk about economics with EFS. As I mentioned earlier, with EFS, you pay only for the storage space you use. There's no minimum commitments, no upfront fees. You don't pay to provision storage. There's no throughput charges, request charges, none of that. It's a simple, flat gigabyte per month charge of 30 cents in our US regions. So how do you put that 30 cents per gigabyte per month into context? Well, one way to do that is to think about what it would cost to have a shared file system that you run on your own on AWS. And a common way to do that would be a third-party file system layer that you run on EC2 instances, and that's backed by EBS volumes. And so in that type of setup, you would have, if you're doing this across multiple AZs, so that you get the multi-AZ characteristics of EFS, you would have one instance in each AZ that's running this shared file layer, and you would have two sets of EBS volumes, one set in each AZ that actually stores the data. And you would have inter-AZ traffic between the EBS volumes in order to replicate the data across AZs. So how much would that cost? Well, let's say that you need to store around 500 gigabytes of data, and you want multi-AZ because you require high availability, high durability. So using that shared file layer on top of EBS, you'd probably provision around 600 gigabytes worth of EBS volumes. That's assuming around 85% utilization. You would never 100% utilize an EBS volume. And keep in mind, you'd need to replicate those volumes to the second AZ. So for storage, you have 2 times the 600 gigabyte GP2 volumes. That adds up to $120. You have the compute costs, and these are the EC2 instances that just manage the file system layer. So these aren't your instances that are accessing the file system. These are the ones that are just running that file system layer. And then you'd have the cross-AZ or inter-AZ data transfer costs for all of the replication traffic you're doing. and that $129 per month is if you were doing the typical amount of traffic that we see customers doing on EFS. So altogether, you're looking at a price of about $600 per month to have this set up. On EFS, with a 500 gigabyte file system, you're paying $150 per month. So that's one lens through which to look at the price and understand the economics. And now I'd like to talk about some upcoming features and announce a feature that's available today. So first of all, we are releasing soon encryption of data at rest. And what that will do is it provides an additional layer of protection for your data and helps you meet your organization's regulatory and compliance requirements. And our encryption of data at rest will be fully integrated with AWS KMS, or Key Management Service, so you can manage the keys that you're using to encrypt and decrypt your file data. And the encryption and decryption is handled transparently. All you do is you specify that for a file system, you want it to be encrypted, you specify the key, and EFS manages everything. And there's no extra cost for enabling encryption. So that feature is coming in early 2017. Also coming soon is a simplifying feature for using EFS. Today, every mount target that you create has a unique DNS name, and that DNS name is derived from the AZ in which the mount target resides. With the new feature that will be coming soon, you will have a single DNS name for your file system, so a single DNS name across all of your mount targets. And that DNS name will automatically resolve to the IP address of the mount target and the AZ from which you are mounting your file system. So it's simplification where you don't have to worry about which AZ your instance is in when you're mounting the file system. And to give you a feel for what that will look like, today the DNS names have, the first part is tied to what AZ you're in. That will go away. And now your DNS names for your file systems will just have, your files will just have the rest of the DNS name without that AZ. So your file system ID .efs.region .amazon AWS. And then before talking about the next feature, which is the one that we're announcing today, let me set the stage by talking about how customers typically think about bridging data between on-prem and EFS. And customers typically think about 4 scenarios for working with file data across their on-prem environments and EFS. So one is migration, where they want to move their entire data set in their application onto AWS, and then run the application on EC2 instances using data in EFS. So that's migration. Another is bursting. And with bursting, the pattern is that you would move your data stored permanently on-prem. You move it onto EFS in order to do some processing on the data. So you would spin up an EC2 cluster, do some processing on the data, and then you would move it back onto on-prem to permanently reside there. So that's bursting. The third is tiering, where you would store part of your data set permanently on EFS and keep part of it on-prem, and you would access the entire data set from applications running on-prem. And so you would ideally keep your hotter data on-prem, where it's closer to the applications, and the rest of your data set on EFS. And then finally, there's backup and disaster recovery, where you maintain a copy of your full data set on EFS. You periodically make sure that that's up to date, and then you can use that either if you want to restore backup or for disaster recovery scenarios. And what we're announcing today is access to your EFS file systems from on-premises servers over Direct Connect connections. And for those of you who aren't familiar with what Direct Connect is, AWS Direct Connect establishes a private network connection between your on-prem environment and AWS, bypassing the internet entirely. One of the benefits of doing that is that you get improved latencies on this Direct Connect connection compared to a connection over the internet, and you get improved throughput. So with this feature that we're announcing today, you can mount your file system from an on-prem server using the same NFS 4.1 mount command you'd use from EC2 instances, and you'll be able to access your data just like you would from EC2. In terms of the scenarios that I talked about that this supports the migration, the bursting, and the backup and DR scenarios. Probably not a great solution for most tiering applications because you'll want your hotter data to be on-prem still for those. So this is really about moving your data in and moving your data out. Now keep in mind that the latency of direct connect connections will impact performance. So due to laws of physics, on some direct connect connections, you'll actually see tens of milliseconds of delays due to propagating the data over long distances. So if you're really trying to drive high levels of throughput, high levels of I/O, keep in mind what we talked about earlier in terms of parallelizing the data that you're copying over. And this actually shows a test that we ran that shows the time it took to copy 26,000 files to EFS as a function of the number of threads. And as you can see, as you increase the number of threads, the time goes down, and it has a nice asymptotic nature to the curve, and that's because as you increase the number of threads, every time you increase the number of threads by 2, you're having the time that it takes to copy the data over. So you would expect an asymptote. And this direct connect feature is available today in 3 regions. It's available actually starting right now. So US West Oregon, US East Ohio, and EU Ireland. And then it's coming soon to US East Northern Virginia. And that's it. We are out of time. I do want to encourage you, if you're interested in learning more about EFS and especially learning about some example applications, customers using EFS, there's a case study with Atlassian. It happened earlier today, one session, but there's another one at 12:30 on Friday. And they're talking about Jira on top of EFS. There's a case study with Spokio. They're talking about web serving and optimizing web serving with EFS. And then there's a session with Monsanto where they're doing a bunch of really cool analytics workloads on EFS. So thank you all. Daryl and I will stand by for questions.